Okay, hello everyone. So we're going to be wrapping up cache memory with a question that actually came in last year's paper. So we have considered a computer system whose word addressable memory, and each word is 16 bytes. Assume a cache which is fully associative, right? Assume a cache which is fully associative, and the size. Assume a cache which is fully associative with tag size 8 bits, right? And block 64 bytes, right? If the same cache is changed to a two-way state associative mapped cache of 512 bytes that uses FIFO replacement algorithm, how is the main memory address split into the tag, set, word, etc., etc., right? So how are we going to start off with this question, right? First of all, we're going to list off our data, right? First of all, we have our memory, right? We haven't been given the size of our memory here, but what we have been given first of all is our word size, which we're going to use for a lot of stuff. We can start off by saying our word size, okay, our word size is equal to 16 bytes, right, which is equal to 2 to the power 4, right, which is just equal to one word, right? So each word is 16 bytes. Then now we have our block size, right? Our block size, our BS is equal to 64 bytes, right? 64 bytes. What are we going to do? First of all, we're going to convert this. It's 2 to the power 6, right? Should be 2 to the power 6. Yeah, 2 to the power 6, right? 2 to the power 6. This is equal to 2 to the power 6 divided by 2 to the power 4, which is 2 squared words, right? So basically we have 4 words, right? Each block can store a maximum of 4 words, right? And then our tag is equal to 8 bits, right? 8 bits. So first things first, we have 8 bits for the tag, and then we have 2 bits for the word. Okay, then now we have our cache size there, right? We've been told that our cache size, our CS, is equal to 512 bytes. Bytes like that. We're then going to divide this by 16, right? Dividing this by 16 gives us 512 divided by 16, which is 32 words, right? You can store a total of 32 words, which is 2 to the power 5, which is 5 bits, right? 5 bits for the word, right? We have oh sorry, 5 bits for our cache size, right? For our cache size. Well, no, not 5 bits. But yeah, kinda. Okay, so now what we're going to do here is we're going to say, firstly, we're gonna say our cache size, right? Because what we want to calculate here, the first part of the question is we want to calculate how this memory is split into tag, set, and then word values, right? So we know that first of all it's a two-way set associative cache map, right? So our cache size there, right, is equal to first of all our k times 2 then d plus w, right? d being d being our set bits, then w being our block, and then k being our mapping there. So you have 2 to the power 5 being the size of our cache. This is then going to equal what is our k? Our k is 2 times 2. We don't know what our set bits are, but we know what our word bits are. What are 2? We have 2 bits for our words. This is power 1. This is just 5 is equal to 1 plus d plus 2. Hence d is equal to 5 minus 3, which is 2, right? So our set bits equal to 2 there, right? We have 2 bits for our set. And what is our tag? So since we already know that our word is 2 bits there, the only thing we're going to do is that we're going to just subtract those 2 bits from our original tag, because this was the fully associative map, right? So we're going to subtract those 2 bits from there, and which we're going to say 8 minus 2, which is 6 tag bits. Hence, we're going to then conclude, right? We're then going to conclude to say our physical address, right? Our physical address is split into the following cases. We have 6 bits for the tag, 2 bits for the set, and then we have finally 2 bits for the word. So this is tag, set, word, right? Tag, set, and word there, right? So basically that's how that is split up, right? Okay, what is the next thing? The next thing is the number of blocks, right? The number of blocks. How do we find the number of blocks? Well, the block bits is just these guys over here. These are just the block bits. Or you can say the block, right? The block is equal to the size of our memory size, which is in this case 2 to the power 10, because we have 10 bits overall, divided by the size of our words, right? The size of our block there, which is 2 bits, which then just gives us 2 to the power 8. What is 2 to the power 8? This is 256. So we have 256. We have 256 blocks altogether. So that's how we calculate this one over here. Okay. So we've talked about how to find the physical address split, and then how to calculate the number of blocks. Now we're going to go into this part of the question, which is when the program is executed, the process reads sequentially, right? It reads these as follows. We have 15, 12, 27, 28, 28, 24, and all that stuff there, right? So what we want to do here is we want to, first of all, for all the above accesses, right? For all those accesses, we want to indicate whether the access is a hit or a miss. So what I'm going to do in this case is I'm going to do it manually as opposed to the way I did in the table previously, just so everyone can follow along a bit better. So first thing we're going to do, right? Going to erase this part for now, right? So we're on this part of the question. First of all, we have our access number 1, right? Let's see, number 1. What's access number 1? This is a 15, right? 15 in binary in 10 bits is 0, 0, right? Then we're going to have 0, 0, 0, 0. Then I'm going to have 1, 1, 1, 1. So 1, 2, 3, 4. We have a total of 10 bits there, right? So first of all, this is a miss, right? This is going to be a miss. Why is this going to be a miss? The reason this is a miss is because the cache is originally empty, right? We've even been told in the question to say, what was that part above? Assume the cache is originally empty. We've been told this part here. So the first one is always a miss, right? Then we're going to load in, right? We're going to have to load in the blocks that this one comes with, right? So to do that, we know that this one over here, right? If we start counting in binary of 0, 0, 0, 1, we have 1, 0, and then we have 1, 1, and 15 is here, right? So to subtract a 1, we're going to have 14, here we're going to have 13, then here we're going to have 12. What this is basically the other lines that what's this? That memory address 15 is already. In short, this is the block, right? This is the block that 15 is in, right? Because we have been told here to say this is 1, 1, so it is the 4th line in its block. So the other words in the block are 12, memory address 12, 13, and 14 there, right? So we're going to get these and then load them into memory. Now, where are we going to load them? We're going to load them into, first of all, this part here, right? This part here specified by our what? By our set bits, because remember our set occupies 2 bits, right? Our set occupies 2 bits. This in binary is 3. So what we're going to conclude here is to say we load from 12 to 15 into we're going to load all of that into set number 3, line 0, because remember this thing has 2 lines per set, right? Then I'm going to move to access number 2. Access number 2, we're loading a 12. This is a hit because we just loaded it in there. Next thing is number 3, right? Number 3, what we're getting is a 27. Remember our cache was originally empty and we haven't even loaded in this guy, so this is a miss. We convert this to binary, which is 0 0. Right, this is going to be 0 0 0 0 0 1. Right, then we're going to have 1 1 0 1 1. Right, so this is the binary representation of number 1 2 3 4 5 6. I've added an extra bit, haven't I? 1 1. Yeah, there's an extra bit, which is this. Yeah, okay. 1 2 3 4 1 2 3 4, and then 1 2. Okay, yeah. So this is going to be 16 plus 8, which is 24, plus 3 there, which gives us our 27. So first of all, this guy over here, this is a miss. So we're going to have to load it into cache. So we're going to only be concerned with these 2 bits here, these 2 sets of bits here. First thing is this one. What's the value for this? The value for this is 2. So we're going to load it into set 2, but which blocks are we going to load in? Same thing we did here previously, right? Same thing we had done here. We're going to say 27 is at this block over here, right? 27 is at this position in our block. It's at position 3. So then we're just going to count downwards to find the other positions. This is 26, 25, 24, right? So what do we do is that we load 24 to 27 are loaded into what's the set? This is set number 2, set 2, line 0. So we're going to load that into set 2, line 0, right? Then now we're going to go to access number 4. How many accesses are in here anyway? 8. Okay, halfway. Well, access number 4. Access number 4, 28. We haven't loaded in 28 yet, right? So this is automatically a miss. So I'll load in 28, which is a miss, right? It's going to be a miss. So what do we do? First of all, we convert this 28 into binary, which is going to be 1 1 1. Then we're going to have 0 0, and then the remaining here is going to be 1 2 3 1 2. So yeah, that's it in 10 bits. Okay, so now what we're then going to do at this point is say first of all, we determine which block it's in, right? Which position it is in the block. At this point it's at position 0 0. So if we draw that thing again to help us, 0 0 0 1 1 0 1 1. So 28 is here. So the next one will be 29, this one will be 30, this one will be 31, right? To be loaded in with this block. And then which set is it going to go into? It's going to go into this set, which is set number 3. So what we're then going to do is that 28 to 31, right? To 31, these go. So go to set 3, line what? So I'm going to let you guess what line does this go to. It goes into line number 1, because remember each of our sets has 2 lines, and initially here set 3 we occupied it with this block over here from 15 or from 12 to 15, right? We occupied it with this block over here. So meaning the next time we put something in, it's going to go into line number 1, right? We're going to load that. Then now we're going to go 5, which is 29. This is going to be a hit. Why? Because it was loaded in over here, right? Then we're going to go access number 6, right? Access number 6 is 44. Like that is 44. 44 converting this guy into binary, it's just 1 0 1 1. Then we're gonna have 0 0 0. It's going to be 12 plus 32. Yeah. Then 1 2 3 4 5 6 7 8 9 10. So it's that in binary. So first of all, the block it's in again, so I'm going to erase these guys. So 44 is here. This is going to be 45, 46, 47, right? So meaning the block is going to be loaded in to be from 44 to 47, right? Which set is it going to sit in? It's going into set 3, right? But now here we have a problem. Set 3 is already full, right? Set 3 is already full because we've loaded in with this block, right? The one I just from calculating this one over here, and then this other block here that we did at first. So how do we replace that? So we go to the replacement algorithms, and we've been told that the cache is a first in first out algorithm, right? Let me even highlight. This is a first, supposed to be highlighting, I'm doing something else. It's a first in first out kind of algorithm, right? This is what we want to do. So first in first out basically means the first thing that was the thing that has been there the longest is what will leave, right? So if we look at this, the one that we added there the longest was this one over here, this block from 12 to 15, right? Followed by, of course, this one over here. So this one from 28 to 31, we just added it in. So the oldest one there is 15 to us is this one. So we're going to replace the contents of line number 0. So we're going to say 44 to 47 are loaded into set 3 line 0, right? Let's switch back my pen. We're going to have access number 7. So access number 7, is going to be for 15. This is going to be a miss. Oh, this one was a miss as well. This one is also going to be a miss. Why is this going to be a miss? Remember, we just replaced the contents of this one. We're just going to replace the contents of set 3 line 0, which are 12 to 15, right? We just replace those contents with the block of 44 to 47. So this is going to be a miss. So what do? We then load back that block of 12 to 15, right? They go into, now they won't go into line 0. They'll go into set number 3. But remember, the one that has been there the longest now is this one over here, that's line 1, because we just replaced the contents of line 0. So the one that has been there the longest now is this guy over here, which is then going to go into set 3 line 1, right? Next thing we're going to have is access number 8, which, what is at access number 8? Access number 8 is 43. Have we loaded in 43 anywhere? No, I have not loaded in 33 anywhere. Or 43. So what I'm going to do is I'm going to convert that into binary real quick, which is 1 0 1 0 1 1. Then we're going to have 0 0 0 0 there, right? We're going to have this content over here.